All right, welcome back. We are COMP2142. That's Game Artificial Intelligence 1 and the Winter 2026 semester. And this is week 5, part 1, broadcast and recording. This week, as mentioned, I'm supposed to be in person, but I'm remote asynchronous, so I'm missing all you guys. This week is also the first week we talk about data structures. One thing that we don't have in our program, which is something that Wallace and I have been addressing in terms of program adjustments and renewal, is a data structures and algorithms course. We don't have a dedicated course to that. So what we're doing is we're fitting in some of that stuff into this course because you need some data structures in order for you to do AI behavior. Without data structures, then AI behavior becomes very difficult to talk about because you may not have the background knowledge for that. So we're going to start with data structures today. And I will give you a bit of a challenge as well. Hopefully you guys can try it out and see how that works for you. And I'll kind of start one of the challenges with you, but then we'll do some of them together. We're also going to be working on obstacle avoidance part 2. We did last week, we kind of set up an enemy pawn. That's what we did. And then because assignment 1B requires obstacle avoidance, I'm going to give you most of the algorithm that you need, and you need to execute it. And then a couple of short weeks from now, there will be our midterm, which will require you to do something as well, similar to what we've been doing with the same project. So again, you have to use the project that I'm going to build up until then. So it's going to build up to the week 7 project, and then I'll give it to you. One thing that I may do, only because I'm delayed, like currently I'm broadcasting at around 1 p.m. on a Saturday, and this is supposed to have done this yesterday. I may extend everything else out just one day or so, just to be fair, and that way it'll give you a chance to consume some of this information and use it for your assignment 1B. All right, so that is what we're doing. We're really looking at an intro to algorithms and data structures today. We'll talk about big O notation, what that is. We'll talk about some common runtime functions and how we meter our algorithms to make sure that they're efficient. We'll review collections and generics. You may or may not have had a lot of information about this. Currently, we talk about this in like Game Programming 1, which is like, hey, this is what a collection is, this is what generics are, and so on. And then we'll start with the first data structure we're going to start with this week is sorting algorithms, how to sort stuff, and that kind of thing. Then our lab focus will be on obstacle avoidance part 2. We'll add whiskers to our start pawn, which will allow us to detect collisions, and that's part of what we're going to do. We talked about obstacle avoidance using these whiskers, raycasts basically, that can detect obstacles along the way, and we're hoping that we're going to get information from our whiskers, so that way we can turn one way or the other. So that's what we're doing this week. Let's begin. So let's talk about data structures and algorithms first, and then what I'll do is I'll take a short pause after we talk data structures and algorithms, and I'll get right into our discussion about obstacle avoidance. Okay, so let's do this. So what is an algorithm? And this is kind of a key thing to think about. We've been hearing about algorithms the entire time. Heck, using our Rubik's Cube, that's an algorithm, right? Learning how to do this. Again, just a reminder that there will be a bonus lab. It will be worth 5% of your final grade, and you can use it on any one of the 3 courses that I'm teaching you this semester. So it could be on Game 2004, which is basically level design. It could be on multiplayer, which if that's your weakest part. It could be that you're going to use this on this course because maybe this is your weakest course. But learning how to do the Rubik's Cube, and if you already know how to do it, that's awesome. I just need you to prove it within 3 minutes. If you can do it under 3 minutes, you'd have to record this thing live, so no cuts and whatever. So you mix it up nicely, and then what you do is you solve the cube. Solving the cube is not, a random thing. Okay, I mean, sure, you can come to it randomly, but most likely it's like something that you've already thought about, and it's an algorithm. So you follow the algorithm. Start with a mixed cube as an example. Here we go. And then what you want to do is you want to solve this thing, and solving it is basically just going through a pattern, right? Which is kind of what an algorithm is. It's basically a way of solving a problem but you're using a pattern to do it, right? And the pattern that you're going to use is basically, something that's repeatable, right? A repeatable pattern that you're going to use over and over again to solve the problem, which is from a programming perspective. That's what you're trying to do. And a lot of times, the problem that you're trying to solve requires code, right? And the code can rather, ugly. And I mean that in terms of, like, if you were just solving a brute force and you didn't really know had an approach to take when you're solving a problem, then it could be actually very long, and you could be taking the wrong approach. Sometimes you could write yourself into a corner, so to speak, because you've just never done this thing before and you're trying stuff out. Now, it's not a bad thing, because I can talk about this as well. When we're talking about coding, at the end of the day, what we want to try and do is we want to experiment, we want to fail, and we want to make it work. So I always say, make it work and then refactor. That's kind of my philosophy on things. Because if you don't have working code, who cares if it's efficient, right? If it's efficient, it doesn't work. Meh, it's not important. The more important thing is that it's working code. And I think that's the thing that we want to emphasize here. And to make working code, you need to really have a plan. And that's what these algorithms allow you to do. They give you a plan to follow. And, at the end of the day, right, when we get to the point where, you have something that is repeatable and something that is doable in a reasonable amount of time. So then we have data structures, and data structures allow us to create our algorithms. A lot of times it requires a storage container. Say an example would be an array, or a list, or a dictionary, or a map, or something like that. And you have to know what those things are. So what is a list? How do you make that? Well, really, if you think about it, what a list is basically an array that is managed. Because an array is basically unmanaged data. That's all it is. It's just basically contiguous memory locations, one after the other. That's really what an array is. And a list is just something that has more structure around it. That's what that is, right? Here's a bonus. What about design patterns? We've talked about this before very briefly. And I'll talk about it again with you guys. Remember we talked about this earlier this semester. We said that design patterns, the group of four, right, back in the 90s, made a bunch of design patterns. And it was done with OOP, right? So object-oriented programming design patterns is what we're talking about. And when we're talking about, these kinds of design patterns, they're repeatable solutions to common problems. That's what they are. So instead of you having to come up with these patterns on your own, they found these 23 design patterns solve most of the problems that were out there, as opposed to you having to go and find a kind of a repeatable solution yourself. Because at the end of the day, what you don't want is for you to spin your wheels when it comes to coding. So we have to be able to manage our algorithm somehow. And one way that we've come up with that is this idea of big O notation. So it really describes the theoretical performance and of an algorithm, right? And so we can think about algorithms, common algorithms, and common things, ways of doing things, components of our algorithm even, as an example. And what we want to be able to do is kind of create a measurement for things like how long does a for loop take to do things, right? It's very, very quick. What about nested for loops? What about 3 nested for loops, as an example, and so on. And the more of those kinds of structures you use in your algorithms, it actually can take quite a bit of time. So usually big O notation has some kind of function to describe the algorithm's worst case scenario when it comes to performance, right? And this is sometimes called the program's asymptotic performance. And what we want is we want to use the function O. So O represents the function that's involved. It's almost like a curve that's created by the type of code that we're using, right? So sorry, and I'm taking time because I'm trying to talk and do this at the same time. It wasn't exactly 3 minutes, but that's only because I was distracted by talking and trying to do two things at the same time, which generally none of us are really great at, but it's done. So that's what the big O notation means. Big O notation just represents the function. So you can think about it as an anonymous function right now, but n squared is the type of the result of the function, which means it increases the square of number of inputs. So for example, if I have an input 2 to the power of 2 as an example, or 3 to the power of 2, 3 times 3 is 9, and so on. So it's kind of like this exponential function. That's what this means. So we start with the bottom, the most efficient functions that we can have, and that's usually constant time. So O of 1. So, and a good algorithm is an algorithm that's O of 1. If you can find something like that. So here's examples of constant time. Finding if a number is even or odd, constant time. Check if an item, on an array is null. We can check to see if it's null. Print the first element from a list, right? And find a value on a map. So if I go do, key value pairs, and let's say that's how a map is, or dictionary, and if I pass in the key, it gives me the value. That is O of 1, or constant time. Let's go to one level worse than that, which is logarithmic time. So logarithmic time is O of log n, and it typically divides the number of items it must consider by a fixed fraction every step, right? That's what happens. So it's not so bad. So here's examples: finding a word in a physical dictionary, finding a person on a phone book, or finding the index of an element in a sorted array, kind of thing. So if it's a sorted array already, it's easy because it's in order, right? So in order, kind of like search, as a good example of a logarithmic function. Linear arithmetic. Okay, this is the next one. Suppose an algorithm loops over all the items, in a set, and then for each loop performs some kind of function. Then that's n log n, right? Performance, or linear arithmetic time. Examples of this would be, an efficient sorting algorithm like merge sort or quick sort. We'll talk about those soon. Some kind of nested looping structure. So 2 for loops, as an example. A for loop within a for loop, that's linear arithmetic time. Okay, that's what we talk about. Again, each of these that I'm talking about is progressively worse in terms of measurement. Okay, quadratic time, O to the n squared. That was the first thing we talked about, or exponential, if you will, right? So here's one. Check if a collection has duplicated values. That's tough to do, right? More difficult than looping through things, because you have to have a bunch of stuff that you're checking. Sorting algorithms, for example, using a bubble sort, insertion sort, or selection sort. We'll talk about some of those today. And then finding all possible order pairs in an array, right? Like more complex. You can see the complexity keeps on getting higher and higher for what we're trying to do in terms of the algorithms we're making here. Here's exponential time, 2 to the n, all right? So I was actually talking about quadratic time before. So a good example is, the power set, finding all subsets on a set. Okay, so if you remember what a set is, set of all values, as an example, that might have some criteria, finding all the subsets on a set. So example, if I said, the set of all boys wearing green shirts, as an example, and there might be green shirts and blue shirts, as an example. And I want to categorize those two things. That's exponential time, Fibonacci sequence. So that's 1, 1, 2, 3, 5, 8, 13. Calculating the Fibonacci sequence, that's exponential time. The traveling salesman problem, right? Using some kind of dynamic programming, which means, and I don't know if you guys have ever heard of the traveling salesman problem, but it's basically a classic algorithm to solve for computer science, which is I have a fixed number of cities, in a map, and I can only ever travel to a city once. That's the traveling salesman problem. But remember, the links between cities, and in this particular case, there's only certain ways you can travel through each city to get to another city. As an example, I'm thinking about this as nodes on a graph. So this is kind of our exponential time. The knapsack problem, which is another type of a classic problem. Take a look at this. If you look at the traveling salesman problem or the knapsack problem, it's interesting how they, kind of the challenges they put to computer studies students to kind of figure out how these things work. Factorial time. This is the next level. So O to the n factorial. The factorial function, which is written n to the with an exclamation mark, or n factorial, is defined for integers that are greater than 0. And basically what it is like, n factorial is like 1 times 2 times 3 times 4 times whatever to the n. So if I said something like, 3 factorial, it would be 1 times 2 times 3, as an example. And then the function grows much more quickly than even the exponential function, because it's much steeper curve. So this is things like permutations of a string. I have a string of characters, and I want you to figure out all the types of permutations of a string. That's n factorial. It's a factorial time. Solving the traveling salesman problem with a brute force search. So way worse than a dynamic function. All right. So this is kind of a very bad way of doing things. There's a bit of a chart, and I've provided you with a link, and the link is cool because it talks about big O complexity, and here are the worst ones. So anything that's O to the n squared, which is the exponential time, quadratic time, or O2 to the n, which is exponential time, or O n factorial. Once you get into these areas here, it's very complex and very bad in terms of performance. You want to stick with at least linear arithmetic or logarithmic time, as an example in this area here. And of course the best one would be logarithmic or constant time. Okay, so that's kind of the way to look at this. If it's something up here, you don't want to do that very often, And there's some examples of common data structures here, which is pretty cool, this little link, in terms of how they are from a complexity and performance perspective. So accessing an array is O to the 1, which is constant time. Searching an array is O to the n, okay, which is pretty good, right? And then you can see that it's, you're good for using arrays. So arrays in general are preferred from a data structure perspective. If you can make things with your own array, as opposed to use something like a list, then it's better. And the reason why is because a list is just a managed array. So someone else has written that stuff, and using those convenience functions actually makes it, worse from a performance perspective. Then there's stacks and queues, and we're going to talk about these structures. By the way, each of these things is clickable, which is really cool. So if I look at stack, as an example, it talks about what a stack is, right? So if you don't know what those are, you can kind of look them up just clicking on them. But basically a stack is similar to like a stack of cards or a stack of plates. And the idea with the stack is that you add and remove elements of the collection, because these are all different kinds of collections here. That you can add and remove and all that kind of stuff by whatever's on the top of the stack is what you pick off the stack. So it's last in, first out. The last thing you put on the stack is the first thing you pick off the stack, as an example. A queue is the other way around. A queue is a lineup, right? It's first come, first serve, or first in, first out, right? That's how it works. So you line up to get a coffee, as an example, where the first person that lined up, he's the one that's going to, or she is the one that's going to get served. But the last person that lined up has got to wait. So that's how a queue works. Again, stacks and queues, fairly efficient in terms of time. Okay, so they're not terribly bad overall, right? And that's pretty good from a performance perspective. Then there's linked lists. Linked lists we're going to be talking about are nodes that are linked together where you can traverse from one member of a list to the next. So typically when we make a list, right, it's a linked list. You don't know it, but that's how it works. And a doubly linked list, you can actually go back and forth. There's extra members, data members, that allow you to go to the previous node or the next node. That's a doubly linked list, right? And there's other ones here that they talk about as well. As you can see, as we get more and more complex, for example, a binary search tree, we get more complex, but it's still not bad. Log to the n, that's logarithmic time, as an example. Where it gets bad is sorting and searching algorithms. Okay, so things like a quick sort is O(n) log n. Okay, so again, it's not terrible. It's logarithmic time, linear arithmetic time, as an example. But where we get bad is things like the selection sort. So any of these red things here, or redder ones, is bad. So quick sort's pretty good. And they always talk about the worst case scenario. So there's like the best case scenario from a time complexity, the average case, and the worst case. In the worst case, it can be, O to the n squared, as an example, which is quadratic time, right? That's the worst case scenario, right? So that is things they talk about. One thing that you also think about here is the same thing with arrays. You can see that the average, this whole area here is the average access, and this is the worst case scenario right here for what we're doing in terms of access, searching, insertion, and deletion. You can see that insertion and deletion is more complex than just simple access. Okay. So same thing. So you can see some algorithms that are pretty bad, and some algorithms that are much better. So there's a lot here that you can take a look at. And there's lots of stuff out there that can help you kind of assess what you're doing. But the first thing we want to talk about is, when we speak together, is how complex do you think this thing is? And if you put things together, like for example, you have lots of for loops, you have, one of those, then you can almost estimate, and approximate what your complexity is going to be. Okay? So that is big O notation. What I want to talk about briefly now is this idea of collections and generics. Okay, so there are two types of collections, and I want you to think about this as, and these are the bases, or the fundamentals for data structures. If you think about them, we can't really have a data structure, for example, a tree or a graph, without having some kind of collection to hold that data, right? So again, there are two types of collections, containers, if you will. One of them is a linear collection, and the other one is nonlinear. Okay, let's start with linear collections. So a linear collection is a kind of a list of elements where one element follows the previous element. A linear collection, right? And so things like an array, right, as an example, is a linear collection. Stacks and queues and lists are other examples of linear collections where anytime you have an index that starts at 0 and goes up from there, typically a linear collection. All right, so again, very, very straightforward way of thinking about this. Everything has an ordered position in a linear collection. Nonlinear collections are things like this, trees, as an example. And this is a good example. If you look here as a tree, the root of the tree, we'll talk more about trees in another lesson. But basically here you have the root of the tree, and this is a binary tree. You can see that there's only two children or two nodes for each, for each node. Each node has two subnodes or two children. So there's a parent-child relationship. This is the root, and then as you go down from each side, you can see that there's more children. There's different types of children that we're going to be talking about. Children that can also be parents, and children that are just leaves. Leaves basically don't have any children at all, right? We can also kind of talk about a tree as having siblings. So for example, B and C are siblings, right? And their parent is A. There's different levels from a tree perspective, and levels denote how many connections there are from one node to the next. So for example, here, level 0, you're at the root. Level 1, you have one connection. Level 2, there's two connections, and so on. And these connections are things that we're going to be talking about later. So collections, whether they're linear or nonlinear, have these properties, that are part of them. So for example, the length is a very typical property, or count. Sometimes they're called length or count. I want to be able to know how many items are in the collection. So example, how many items are in an array or a list. There's the example. That's the count, and it's something that's part of the collection itself. Now, when we're not accessing, but we're enumerating something, we're kind of counting how many, it's still pretty much constant time when it comes to counting how many items in a collection, as an example. It's not that bad. But once we start doing things like insertion and removal, right? Clearing, that's just one single for loop as an example. It's not bad in terms of the way things work. Okay, so typical methods include an adding, an insertion, a removal. I want to be able to check to see if it contains. This is actually a search algorithm. That's what that does. And then index of. These things are less efficient. Anything anytime I want to do sorting, searching, or something like this, then it's less efficient than these ones. These ones here, this one would be the easiest to do, an add. That's almost I would say linear time, if you will, or O to the n. And then insertion and removal is pretty much linear time for these kinds of things. Clearing, same thing. But once you get into contains and index of, now you're talking about logarithmic time, which is something that happens at the very best, right? Worst case, removing, clearing, well, removing is not bad, but insertion, contains and index of is, it can be quadratic time, worst case. So there's two types of, if we look at the two types, so linear and nonlinear, we can also think about different kinds of ways of accessing collections. There's direct access or sequential access. Sometimes those are the two options that we have, direct or sequential. And nonlinear collections can either be hierarchical or grouped. So there's further categories here that we're going to be talking about. So direct access collections, an array is an example of a direct access collection, where in C# as an example, arrays are not only a built-in data type, but they're also a class in C#, right? So we can use an array to store a linear collection. That's what we can do, right? Adding new elements to an array is pretty efficient, like we talked about. Inserting is less efficient. Deleting is efficient because adding and deleting, we just find the one we want to do. But deleting an element in any other position, so if you want to delete at the end of an array, it's efficient, but any other position is bad, because what happens is then we have to remove that element, because remember, arrays are fixed, they're immutable. So for me to remove an element for the middle of an array, I've got to move all the elements up. That's how it works. That's why it's inefficient to make that work. So another direct access collection type is the struct, and that's why a lot of times we want to be able to use a struct to make our own custom, kind of data type, a struct. Sometimes they're also called structures or records, depending on the language that you're using. And it's a composite data type that holds data that may consist of a lot of other different data types, but it's pretty much a direct access collection. A sequential access collection is a list. So this is where it's less efficient. So again, depending on if I looked at an array, and if I was going to compare an array to a list, the way you access it is slightly different between the two. And it's the reason why it's sequential compared to direct access is because they're not limited in size, they're dynamic, right? Remember, lists are a type of managed array. Once I add management to any algorithm, or any data structure, if you will, then it becomes that much more complex, right? A little bit more complex. And that little more every frame adds quite a bit of load, potentially. Other examples are queues and stacks. So lists, queues, and stacks are about the same, and they're all sequential access. Hierarchical collections, remember, these are nonlinear collections, right? So they're either hierarchical or grouped. Hierarchical is a group of items divided into different levels. So a good example of this is a tree structure where we have a root and we have children. We talked about this earlier. Group collections are like sets, okay? Graphs, networks. So a good example of this, if I have two sets, the set of A, which is these numbers, and the set of B, which are these numbers, and then I want to find the intersection between A and B, that would be 2, the number 2, because you can see that these numbers and these numbers are different except for the number 2. That is where those two sets align, as an example. So that's the intersection. And an intersection is many ways. I'm subtracting everything. That's what I'm doing. Whereas the union is like me adding. Intersection is an and, if you will, right? That's what it is. If I was going to do an and collection, it's almost like A and B, where A and B are both true. Well, where A and B are both true, that's the number 2, right? And a union is where either A or B, which means all the numbers on both sets, right? So that means like both sets are added together to make a new set. That's the union. So union and intersection, is a way of thinking about it. An addition or a subtraction in many ways, right? Another way of grouping collections is, a graph like this. And again, if we're going to do the traveling salesman problem, we had these nodes, and every node represents a city, and we have these connections between nodes, right, as an example. Then we want to be able to traverse from Tokyo to Seattle to London, as an example. We want to find the shortest route from Tokyo to Moscow. Maybe Moscow's a bad example these days, but I'm saying if you wanted to find the closest or the shortest route, then you would have this group collection that you would look at, and anything like this where we have these edges that we want to traverse, that's an example of a group collection. And a good example of using a group collection is using or learning how to use pathfinding, which we'll do this semester. A network is a special type of graph, where edges have a weight. So we have that kind of thing as an example as well, where if I want to go from A to D to C, there's a combined weight of these things that would still be the shortest path, because the numbers here, 72 and 91, are smaller than 186 and 202, as an example, adding together, right? So there are different ways of getting from A to C. I could go A, D to C, or A, B to C, or A, D, B, C, or A, D, B, A, D, C. There's lots of ways of doing stuff. And in many ways, because it's not directed. You don't have a graph like this or a network that has, arrows that tell you there's only one way in or one way out. This is kind of a way of it could be cyclical, if you will, as well, right? So that I just wanted to talk about collections and categorize them, because we're going to be using these collections in making our sorting algorithms, which is the first thing we're going to do. So here's our sorting algorithms. So I want to talk about them next, okay? And then we'll take a short break. So basic sorting algorithms, which is interesting. There are two common operations on a data sorted in a computer, and there are two things called there are sorting and searching, right? So let me say that again. Two common operations on data stored in a computer: sorting and searching, right? So in order for us to search for something, a lot of times we have to sort it first, and that's why we're talking about sorted algorithms or sorting algorithms today. One thing I also want to point you to is this really great article that I found, in the Unreal forums, which is this dude who has basically created all the sorting and searching algorithms here for you, so he can explain how they work in Unreal Engine and how they would look if you were going to do it something like this. And we're going to come back to this, but I wanted to show you this, that someone else has actually come up with that, how to do sorting and searching with blueprints. So sorting algorithms, most of the data we work with in our day-to-day lives is sorted, believe it or not. And we usually sort them by their value or their size. Sometimes we reorganize things. A good example might be a contact list on your phone, right? It's sorted by alphabetically by alphanumeric characters. You could have an online shopping list sorted by their cost. You could do that. Inventory management sorts of hospital prioritize patients with different urgency and priority, and all that kind of stuff. Airports, they sort and deliver luggage in a certain way. So we use sorting in all kinds of real world situations, right? It's a fundamental process, and we need to look at it. So the first type of sorting algorithm we're going to be talking about is the bubble sort. Okay, this is like one of the first ones I learned when I was learning how to program back in the day. And really, it's the slowest algorithm, but it's also the simplest algorithm to learn. And it gets the name because the values float like a bubble, and from one end to the other in a list. And assuming you're sorting a list of numbers in ascending order, so I want to make it from, let's say I have a bunch of numbers, the higher values float to the right, where the lower values float to the left. This is how it is. So This behavior is made because we're moving through the list many times. We're sorting through that list over and over again, and that's why it's called the bubble sort. So the way it works is this: you have two numbers from the numbers inserted into an array. 2 and 72 are highlighted with these two red circles, and 72 moves from the beginning of the array to the middle of the array, and 2 moves from just past the middle of the array to the beginning of the array. All right, so what we want to do is imagine if we had this list, and I want to be able to start sorting the list out, right? So what happens is, eventually, as I continue to sort the list, it moves things, the list around, as an example. So this is the unsorted version, right? And also notice that I don't have unique values in this list. So 72 appears twice at the end, as well as at the beginning. Okay, so that's something that you have to see. And also, it's kind of some random ordering. Some values seem to be sorted in pairs, but for the most part, it's still random, right? So the first thing that this does is it starts moving the higher number, and it starts moving the higher number towards the other end. It kind of looks at the first element of the array and starts comparing. It starts going like this. It starts saying, is 72 smaller than 54? No? Switch. Is 72 smaller than 59? No? Switch. Is 72 smaller than 30? No? Switch. So it keeps going like this, keeps bubbling until it kind of does one of these. Is 72 smaller than 78? Yes, as an example. And this is why you can see that 72 is next to 2. That's the first ordering. And then it goes back to, the next one, the next value, the next value. And it keeps doing that until, until it positions 72 in the right spot. Okay? So I wanted to share with you the bubble sort algorithm. And here's your first challenge if you want to try and do the bubble sort. I've given you the algorithm from a C++ perspective. What I want you to do is I want you to duplicate this, or try your best to have this sorting algorithm work with numbers only. Let's use integers as an example. And I only want you to do this with blueprints. So how do I do this in a blueprint? Okay, because again, a lot of us, I think we don't appreciate the simplicity of doing it like this with code. C++, they're like, oh, C++ is difficult. But I want you to try and do this, in blueprints and see what happens. This is your first challenge. Okay, so try and do this. There's going to be a couple of these, and I'm going to show you at least one of them. We'll work through one of them together, but I want you to do this on your own. It's good practice for you with blueprints anyway. So again, here's the code for the bubble sort, and if we actually go through it, it starts like this. I have my bubble sort function. We pass in an array of integers. Okay, the array is called ARR, ARR, right? And then we say that the size of the array is array.num. That's C++. And then we kind of when the array first comes in, we just store the original size of the array in a number, right? As an example, size. And then what we do is we have a temporary integer holding space, a container that we can hold temporary values. Okay. Why we don't want to do this here, right? And if you think about this here, size minus 1, every single time we do array num, we're actually doing a little algorithm, right? So we don't want to, when it comes to coding, ever do array number or array length here inside of a for loop, because what happens is every loop that occurs, it goes and makes that calculation again. It's actually slower than doing it one time and storing the value. All right, so this is kind of a learning for everybody, right? Because this is what we don't want to do. We don't want to calculate it here. We want to do it outside of the loop, and then we just want to use that value over and over again. So that's the first thing. Here we made a variable called outer, where outer is the size minus 1 of the array, and we check to see if outer is greater than or equal to 1, and if it is, we want to subtract 1, right? That's what this is. We want to decrement this thing. So the reason why we would do this, so it's almost like we have a decrementing number. So a good example is if I have 10 elements in the array, or that I'm checking, 10 elements in the collection, 10 numbers. right? Then I start counting at, the size minus 1. So element 9, the very end is where we start counting first. Okay, that's the first thing. And then the inner loop, right, starts counting at 0, right, where 0 is less than the outer. So we count from one side and the other side at the same time. That's how the bubble sort works, okay? So if my array inner, so example, the array index, if the array inner, so let's say we start at 0, is greater than the array inner plus 1, right, if that's true, then we want to swap it out. And there's usually some kind of swapping algorithm. That's what happens. This little swapping, I don't want to say, let's not say algorithm. Let's call this, the swap, which is a few lines of code. Here's the first thing. We hold our original value inside of a temporary value. And then we'll replace the location in memory where we held that original value with the value plus 1, whatever that value is. All right, that's the next thing we do. And then we take the value from temp and we assign it back to our inner plus 1. So we actually swap those values around, which is what we did when I was talking about here. We moved from 72 to 54. We swapped those two values first. And that's the first thing that happens, okay? And then that's the inner loop. Then the outer loop reduces the size. We do this as an example by, where inner is less than outer, right? So, and we keep incrementing inner until we get to outer, right? Outer would be, let's say, 10, so be less than 9. We do that for all the elements. We'll go through the entire list as an example. And then we keep checking to see if this condition is true. That's what we're doing, okay? And then what we do is we decrement. So we go from, size minus 1, so that it becomes, the outer loop again. We do this inner loop again, but we kind of reduce the size because we've already sorted the last member of the, because we bubble things to the right. We kind of put the highest values on the right and the lowest values on the left. That's what this thing does. So, so here's an example of a small group of numbers to give you more, kind of context. We have this number 7643. These groups of numbers, and the first thing we do is swap 6 and 7. Okay, that's the first pass, right? And then what happens is once 6 and 7 have been swapped, we look at the number 7 and 4, and if 7 is greater than 4, we swap those two numbers out. So now it's like, 7 moves to the 6th location, to the location number 1, and then we move 6 on the other side, right? And then we do the same thing with 4. And we keep doing that until the first pass, 7 is on the right-hand side. Now we do the second pass. So now notice that there's one less iteration. We don't have to touch 7 anymore because it's in the right spot, right? So we take 6 and compare it to 4. If 6 is greater than 4, we swap, okay? And then now we take 6 and we compare it to 3. Is 6 greater than 3? Yes, then we swap. And now with the second pass, we have this, order, 4, 3, 6, 7, as an example. And then the third pass, we take number 4 and compare it to 3. And we say that, okay, is 4 greater than 3? Yes, so we swap, right? And then we say, okay, is 4 greater than 6? No. And so we keep checking. Is 4 greater than 7? No. So then we just leave it the way it is. This scenario is a scenario of worst case. So worst case scenario because we want to sort it in ascending order, and it's already in descending order. 7, 6, 4, 3 is descending from highest to lowest. We want to make it go from lowest to highest, and so this is the worst case scenario starting off. Okay, so that is what happens. The swap function happens many times, and this swap function, we're going to do it together. You're going to see that this swap function in one form or another is part of each of these sorting algorithms. So this is our first sort, bubble sort. The next one is the selection sort. So this is kind of neat. And this works by starting at the beginning of the array, comparing the first element with all the other elements in the array, and the smallest element is placed in position 0, and the sort then starts again at position 1. So it looks like we always put the smallest element here every single time, and then once we've done that, then we go to position, the next position, the next position, the next position. We keep going this way. That's called the selection sort. So a good example is we go, okay, so start at the beginning and we see if this is smaller. So is 72 smaller? As an example? No. All right, well, we have this number in our minds. We're like 72. Okay, so 72 is that smaller than 54? No. Is it smaller than 59? No. Is it smaller than 30? No. Is it smaller than 31? No. Is it smaller than 78? Yes, right? It is smaller, right? And so then, then we look at the next number, which is 2. Oh, well, 2 is smaller than all these numbers. So now 2 becomes the smallest number. And then it's not 77, and it's not 82, and it's not 72. So we don't, have that. That's the first thing. We just select which one is the smallest number. So 2 is the smallest number. So if that's great, if that's good, we take that 2 and we put it at the beginning. That's what we do. And we take the beginning and swap it into 2. So we do the swap. Well, we do it here, where we swap the number that we had at the beginning, the number we held in memory, but we were comparing the entire way, right? And we swap it with 2. That's what we do. Okay, now we do it again. So we go through the list, but we ignore the first one. We don't care about the first one because this has already been sorted. 2 is the smallest number, right? We put it at the left side. And now we're looking for the next smallest number. Well, the next smallest number is 30 in this case, right? Because we go from 54 to 72. The next smaller is 30, right? 30 is here, but we started with 54. That's the first number in the list, just like we did with 72. So now we swap those two out. Cool. Now we don't care about the second number. We work with the third one. So we start here, 59, and we try and find the smallest number between from here to here. And we notice that the smallest number now is 31. So 59 and 31 switch places, and so on until it's done. Now you can see that this takes several iterations for this length of list. So, first, 2, second, third, fourth, fifth, sixth, 7 iterations total for us to sort everything from lowest to highest. Okay, so again, we use 2 loops in the selection sort algorithm. The outer loop moves from the first element in the array to the next to last element, whereas the inner loop moves from the second element of the array to the last element of the array. Okay, and here's the selection sort. So this is the second challenge. Try this one now. So after you've done the bubble sort, try and program this one. Again, notice that the swap is almost identical, right? It's almost identical. Take the element. This swap is something that you can almost save as a own little micro function, little function that we can use over and over again for different kinds of functions. We'll get there in a bit. So that is your selection sort. So the way it works is, again, we manage to get the smallest number, array.num. We store it in a value. And then the min index and the temp are 2 additional integers that we're going to use, right? Here, outer, we started at 0, where outer is less than size minus 1. We increment the outer loop. The inner loop, as an example, we have the outer, plus 1. That is where we start. And we say where inner is less than size, where size is the total length of the array, then inner plus plus. So both of them are incrementing how this works. And if array inner is less than array min index, where min index is the outer, where outer is whatever the first element is, as an example, then min index is equal to inner. Right, that's that index. We're just swapping indices now. We haven't actually moved anything, and then we do the swap. Okay, and we do that over and over again many times in order for us to get this done. So again, a different way of doing things, and this is a little bit more efficient than the bubble sort. Bubble sort's the worst in terms of efficiency so far. The next one is insertion sort. Okay, and it's kind of a way of sorting things numerically or alphabetically. It works kind of the way we sort playing cards in your hands. And what it does is the array is split in half. And we keep sorting things in half and half and half until we have a sorted array. So this kind of cuts things in half, insertion sort. So here's an example of this. So we start again with the length. We have a couple of temporary variables. The outer loop, as an example, is outer is equal to 1, right? We start at the second element. The outer is, while outer is less than size, we increment it. And what we say is this: we start with our temp variable as the outer value, so the first element of the array, if you will. And once we say that, then we say the inner is equal to outer. So inner, which is kind of the kind of this temporary value that we have here. We defined it as, for right now, I didn't have a value, but outer, we just capture that 1, that's the index, so the index is 1. And then we say is if 1 is greater than 0, well, yes, it would be. 1 is greater than 0. And my array inner, which is still 1, because all we say is that for now inner and outer are equal, inner minus 1, that would be 0, right, is greater than temp, where temp is equal to the array outer, right? While this is true, right, then what we want to do is we want to say that array inner is equal to array inner minus 1, and then we want to decrement inner. So this is the swap. Now this swap is different than the other two swaps, but this is where the swap happens, and it's a much more complex swap. The swap uses a while loop for this to happen, okay? So again, it uses two loops, and the outer loop moves elements element by element through the array, whereas the inner loop compares the elements chosen in the outer loop to the element next to it in the array, right? And what it does, again, it splits things in half, okay? Let's talk about time complexity now for these three algorithms we've talked about. Best case scenario for bubble sort, as an example, is O to the n. So that's, kind of linear time, which is pretty good. Worst case scenario, which we saw earlier, so that's reversely sorted, is O to the n squared, which is O quadratic time, which is bad. That's bad, kind of in terms of performance. And the average cost that you're going to find is quadratic time. That's why bubble sort is definitely not a preferred way of doing things. It's not great, okay? But the good advantage to it is if you need a quick sorting algorithm, it's easy to code, right? Disadvantage is it's, again, very poor efficiency. Selection sort. The best case is O to the n squared, all right? So it's actually worse in many ways, than bubble sort. But if it's reversely sorted, or if it's, if it's not reversely sorted, the algorithm comparison is the same. So the average cost is quadratic, and it's quadratic no matter what you do, right? So advantage, it's great on a list of structures, right? You can add and remove really, really great. And it's really good for an in-place sort in terms of memory management. It's low memory. Disadvantage, time complexity is high, right? So that's not good, and it's not scalable. Insertion sort. Best case scenario is sorted array already, and that's like, linear time. Worst case scenario is a reversely sorted array, and again, you can see that this is also quadratic time. N squared, quadratic time. So it's, for the most part, right, if you think about it, in the average case is O to the n squared. These are all quadratic algorithms. Just some of them are better than others. This has a chance to be more of a chance for the insertion sort to be linear time. At least parts, especially if some of the array is already in sorted order, it can be linear time. Whereas if you go back to selection sort, it doesn't really matter how it is. It's always O to the n squared. Here, if it's a sorted array, then it's linear time for bubble sort, and it's easy to kind of put together, right? So advantage, easily made. For smaller values of n, insertion sort performs really efficiently. So if I don't have a very big list, it's pretty good, right? Why is this all messed up? Disadvantage is generally used when the value of n is small, but for larger values, it's pretty inefficient. So that's your insertion sort. So again, if we kind of analyze these three algorithms, best case, average case, and worst case, you can see that for the most part, you're going to use the bubble sort if it's a very simple thing you want to do. Insertion sort a little bit more complex, but with a smaller data set, you're still good. But selection sort is the same. It's consistent the entire way, so it's going to be bad. But there's advantages to using this as well, and it scales a little better, kind of at the top end. But worst case, they're all the same in terms of complexity. Now, one thing we have to talk about before we end this little talk about complexity is that computers are very quick. So even though I'm saying, oh, it's bad from a complexity perspective, back in the day when I was learning how to code, computers were quite slow. So we cared about these algorithms, these efficiency gains. We cared about that a lot more than people do now, unfortunately. And we did that because we wanted to reduce the time it took for something to complete, as an example. Nowadays, with our computers the way they were, comparing our computers to what I had back then, it's like we have supercomputers in our pockets. Like our phones are so much faster than computers that we had, like actual room-sized computers, back in my day, they're literally, like I said, supercomputers. The ability for us to actually do video conferencing and that kind of stuff on the fly was a pipe dream, back when I was growing up. We never thought it was going to exist. We saw it only in science fiction movies. So why am I saying this? I'm saying this because, efficiency is just so much better nowadays. So what happens is, because not efficiency, the computational power of the machine that you have at home, as an example, is a monster compared to what we had before. And so as a result, programmers, they get sloppy because they don't need to be really that great, because the computer will compensate, is the answer. And that's true for most applications except game development. Game development requires us to go back in time a little bit, because what we try and do is millions of calculations sometimes every frame, right? And especially when we do things like ray tracing shadows, and we're trying to render things on the screen and display something that is 3D on a 2D monitor, all that kind of stuff requires many, many calculations. And if we can improve things from a time complexity perspective, this is where it makes really a lot of sense for us from a game programming perspective. Bonus, I want to talk about the merge sort. I didn't give you the algorithm, but the merge sort kind of is another way of doing things, where a merge sort kind of breaks things off into subarrays. So example would be this. We take a look at this array, and we're like, okay, the array length is 4, right? 4 elements. We go to the middle of the array, and now we create a subarray like this, 4 and 2, right? And we do the same thing. There's another array, 6 and 0. And then what we do is, once we have these 2 elements, we're down to this small, we sort them, right? That's what we do. We say, okay, well, 4 goes to here and 2 goes to there. And now we have this sorted value, 2 and 4, okay? And that is our, because again, what we do is we break it down into these little elements. Keep breaking it down until there's like single elements. These are all the single elements here. Like 4, 2, 6, and 0 is when you have individual elements in the array. And then we sort them, so 2 and 4 as an example, and then 6 and 0. And then what we do is, once we have 2 and 4 and 0 and 6, then we combine them back together at the end when we have these 2 things, because this is sorted and so is this. And so now we compare it. We say, okay, well, is my lowest value, is it lower than your greatest value? No? Well, then swap those. And then what we have is, 0 for, 0, 4, 2, 6. That's the next level. And then, okay, cool. So 0, 4, 2, 6 is my my biggest value. Is it lower than your biggest value or whatever? If it is, swap. If not, now we compare the inner values. Is my inner value bigger than your inner value? If it is, swap. And then it kind of comes up with this kind of idea. So it's kind of an interesting thing where we split things together and then merge things together. That's why it's called the merge sort. It's an interesting way of doing things, and the advantage is it's popular because for large data sets, when I split things in half, it's almost a way of working by making the problem smaller and smaller. So kind of another way of sorting. So again, this week we're talking about sorting, and I promised you that we would do one of these together, and I'm going to show you the bubble sort, the most inefficient one, after the break, right? After that, we're going to get into our Unreal Lab, and the Unreal Lab is going to feature a couple things. One, we're actually going to kind of put together everything that we need for our collision avoidance, or obstacle avoidance, what we want to do. But before we get to that, I'm going to bring up my project. This is week 5. And what I want to do is I want to put this up on DevOps for you. So here, let's go to DevOps. We're going to go down to this. And I'm going to make week 5 here by logging in. So you can have my code. So again, I find this kind of stuff really interesting. You may not, especially if you're more of an artist than a programmer. But I think it's important for all of us to understand these things, or at least have heard of big O notation and what's an algorithm and what's a collection, what's a data structure, those kind of things. So here, so it's COMP2142, and in the winter 2026, and it's week 5. There we go. And I have this, but I want to go back to here and make a brand new Git repository. So we'll do that. Wonderful thing about the AI project and the multiplayer project is that they're very small. So it's not so bad, you know, in terms of uploading to DevOps and so on, right? There we go. So if I was going to think about, while this is doing its thing, if I was going to think about, you know, making the bubble sort, you know, and I'm going to try and do this with you, and hopefully you try this challenge on your own, but I'm going to go back to here, and I want to create a new folder here inside of my folders, like so under content, and I want to call this folder data structures. So data structures, of course, can't have a space because it's still a folder. And in my data structures folder, I want to create something called a function library. So if I go here, and if you notice that there's blueprint class, I can create a blueprint of type. So these are the different classes that exist here. So that's not what I want to do. If I go to blueprint, you know, as an example, and I go scroll down, there's one that says function library. So I want to use this function library, and I want to use these functions in other blueprints. So it's not specific to one blueprint. Sometimes I think of a function library as a static class that I can use. So, so blueprint function library. So usually it's like BPF, blueprint function library, or BPFL. Some people use it that way as well. Is what I want to do. So blueprint function library, so BPFL underscore, and then the name of my function library, which will be like, you know, algorithms. Okay. Actually, we'll just call this, you know, sorting is what we want, and we'll say, or sorting algorithms. How about that? If I can spell. So there's my sorting algorithms. And what we want in here, if I open it up, one day, there we go. And if I put this up here, let's just do that. So I'll show you what this looks like. Compile and save. Notice that there is no event graph, right? It's just functions. And because we're making a blueprint library, a function library, the thing about this is that there must be at least one function. In this case, this new function, right? So I want to make a function called swap. That's my first function that I want to make because I know I'm going to use this function over and over again. So we'll call it, swap. Okay. So I might use it for a couple of functions. And so let's talk about the swap. And if I go back to my code to see some of this, not this swap function. This is a different swap. But if I go back to this swap function, notice that this, where I take something and put it into a temporary container, and then I swap the two things around, you know, and then I kind of do it here, where I kind of take that one thing and put it into the other thing and swap things around, right? I want to swap two values is what I'm really doing. Now, because we're, you know, kind of sorting, we're going to assume that for now, for us, to make it simple, we're going to sort integers. Okay, we're not going to sort floats or any other thing, just integers. By the way, you can apply the same sorting algorithm that I'm going to show you here to anything, whether you want to compare, as long as it can be compared, characters or whatever, or if you make your own comparable, a way of comparing the two things yourself. But for now, we have some value, and we're going to, or value A, and we want to swap it with value B. That's kind of the idea behind it. So we need these two values, swap A and B. And I'm really going to call it that, like A and B. So we have A, and A is going to be, you know, an integer, right? And we have B, and B is also going to be an integer. So those are the two values we get in, out, right? And what we want is when these values are brought in, right, as an example, then we want the values that are going outbound to be already swapped. The values are manipulated, if you will, right? So that's something that's going to happen. So these two values are inbound into the array, but outbound, we're going to have those two values again, right, as an example, but just swapped around. Okay? So we need the outputs again. The outputs are going to be A and B, right? Because we need to be able to kind of send those two values out, right? So sometimes in A and in B is out A and out B might be a good way of saying that. So if I say something like in A, right, in B, and then out A, let's try that first, out A and out B, right? And we just want to be able to swap those values out. So that's the first thing. So we need a temporary value. So again, we need a local variable. We'll call this temp, which will be the integer value. There it is. There's temp. Compile and save. And then what we want to do with this thing when we go in and out is actually do the swap. Okay, that's what we want to be able to do as well, right? So so let's follow this. So temp is equal to inner, right? And this would be the A. We're going to save A, as an example, right? So so first we're going to say that temp, right? So we're going to bring temp in, right? And we want to set temp. So set temp to inner A. So we're going to say get in A, right? And we're going to set this to temp. Temp is going to be set to this value, right? And once we have that, once that we've saved A, then we can set B A to B. So now we can say set in A, set in A. Actually, let's just do that again. If I go to in A, right? So this one, right? I want to be able to set this. Now, one thing to note, right? Right, because I want to, if I say get in A, I can get it. But notice if I say set in A, I can't do that, right? So it's almost like I need to, I'm going to take A and set it to B, right? Because I'm saving A and I'm saying take B and put it into A, right? That's what's happening. So B, out B is going to be set to A. We know that. So it's almost like I'm doing this. That's going to happen right away because I've already saved this, right? So I definitely want to be able to do that. So I'm swapping, right? So then I've got the value of A, right, saved in B, and I want to take A and set it to B. So B, this one, out B, is going to be A. So I'm going to say in A, get in A, right, there it is. And I want to set this to B. So that's going to be happening right away. But B is going to be set to, in B, or out A is going to be set to B, right? But B, is something that we want to be we're putting out. So if we're going to try and do this, really, if you think about it, what are we trying to do? We could, in C++, you would do all these things. Like we would move the temporary variable around. But here, because we're using blueprints, and this is the beautiful thing about blueprints, what we really want to do is this. And that's all that would have to be done. Where we're basically saying A becomes B and B becomes A. That's all that's happening here. So it's kind of a weird thing that we're seeing, right? And we really don't need this temporary variable anymore because we're just doing this. It's almost like a function that basically swaps things around. So that's the swap. Does that make sense? And the reason why I'm asking this is because you think that, you're thinking that things are more complex. And to do something like this, it's exactly what's happening. We're basically outputting B and A. We're having a little function to do this idea. We're putting in, comes in this way, and we kind of out to B, and B comes this out and becomes out in A, and that's all we have to do. So that's the swap function. The other thing that we want to do here with the swap function is now we want a new function. So let's make a new function, and we'll call this, bubble sort. So here's my bubble sort function. Back to bubble sorting. Okay, bubble sorting looks like this. So we need the array number. Well, we get in the thing that we want to sort, which is our array, a T array. T array is the data structure for arrays in Unreal Engine, right? And we get an array, a regular array, and we're having that in. So that's the thing that we need. So bubble sort takes in inputs is an array. So we'll call this whatever that array is. So we'll call this array, right? That's the array that we get in, and it's an array of integers, right? Some kind of array of integers. And if you really want to be exclusive to, or kind of declarative here, because we don't just take any array in, it has to be an array. By the way, in terms of type, these are all the different types that we can use, right? So far, structures, these are different structures that are built in. And these are interfaces and object types. We can decide different object types we can take in, and these are all the built-in enums, right? That's one thing that we can do. Like before, this one allows us to create a set or an array or a single or a map. Those are the things that it allows us to do. So it doesn't really allow us to, create an array of any. It doesn't allow us to do. We can't just choose. There's no any type in here. We have to choose a specific type, right? Okay, so that's the array. In this case, it's just an array of integers. And then what do we get on the way out? We get another array of integers. So this is the unsorted array, right? So unsorted array is out, unsorted array. And on the way out, we get a sorted array, right? And that's the array coming out. So in, unsorted, out is sorted. Okay, that's the thing we need. Okay, let's follow this now. So now the next part is we need the array num. So we'll call it size. So let's make a temporary variable called size. And size is equal to the array. So we can say that get unsorted array. And we want the, and again, if I type length, that's what I want. And I don't want this to be calculated all the time because this is inefficient. By the way, if I say size, it takes me to length, and if I say count, it also takes me to length, right? So Unreal Engine's smart enough to know that any one of those things is going to give me length, okay? Then what I want to do is I want to set the size to this. So that's the first thing I do, because it's efficient for me when I do this thing to have size as one of my delimiters or constraints when I kind of loop. That's the first thing I want to do. So I've got size, and that's this. Temp, we don't need that because temp is only being used for the swap, and we're going to be able to swap inner to outer in a second. Okay, we'll talk about this. Okay, so that's the first thing that's happening. So we need two for loops, an outer loop that counts backwards and an inner loop that counts forwards. Well, how do I do that? So if I type in for loop, right? So you can see that there's different for loops, right? There's for each loops, there's a reverse for each loop, right? And we don't have so for each element in the array is what we're looking for, right? That's a for each loop. If I type in for each loop, there's one thing about these for each loops we get in blueprints. They also give me the array index. For each loops in regular C++ do not. So kind of a for each loop is a very good for loop. If I just type in for loop, as an example, here's for loop here, you can see that we also get the same thing, but we have control over our first index and our last index. Here, we just take the array and we loop through each element in the array, right? So let's see which one makes sense for us. Well, here, if we did a reverse for each loop, then size minus 1 is what the array is going to be. We kind of start at the right side and we go towards the left side all the way till we get to greater than or equal to 1. This doesn't go to 0, right? So it's not where it is, but this one from 0, and if it's less than outer, whatever that value is, and it keeps growing, that's different. So it's kind of like I want to do two for loops, but then let's go back to this for a second. can I do, if I go for loop, right, I can have a reverse for each loop. There's a reverse for each loop, right, where I kind of go from the top to the bottom. I can do those. And there's the other one, for loop. The other for loop that we have is this one, for loop with break. So a break, I can break out. So something that breaks me out of the loop is what this is, the break executable. And when I'm completed, all these things have it completed. I can do something when I'm done looping through the array. So these are the different types of arrays I can use, or sorry, loops I can use. The other one, if I type in a while loop, that is also something that I can do. So these are all the different looping structures that I can use when I'm creating my algorithms, whatever it's going to be. Now, there's a funny thing that we can do. I want control over the first index and the last index, right? That's what I want to do. And I want to be able to loop in a negative direction. I want to make my own for loop. How do I do that? Because none of these really match for the outer loop. I also want to name my loop in a certain way, right? So let's try this. Let me get rid of all these. And let's start with this one. Well, if I right click on my for loop, one thing that we can do, if you look at it, so if I look at all these things here, notice there's go to definition, collapse nodes, which is collapse the selection nodes into a single node, collapse to a function, then there's expand node. How about this one? Does this have an expand node? It does not. How about this one? Does this have an expand node? Notice that this one has something new. It has this expand node. Expand node, be prepared for this, does this, where it breaks in an array, a for loop into this. So this is kind of cool, actually. So this is the input for the array, for the loop. I keep calling it array, but it's a loop. Okay, I'm just going to put this way on the side here for a second. So here's the loop. I want to make this count backwards. Okay, so here's my control. Here's my local integer, which is a variable, right? That local integer is the temporary variable that keeps holding this thing. So I assign this value to the temporary integer, right? And notice that it branches to say if this is less than this. So this, again, if I look at my for loop again, for loop, just a regular one. I have the first index and the last index. This is the last index, this is the first index. So just to show you this, I'm just going to go here and just mark that as first index, just so you understand what I'm doing. All right, so this is the first index. And this is the last index. We're going to make these, do one of these, okay, just so that we can expand this. So this is the last index. And this is also the check. This is the last index and also the check to see what we're doing, all right? So I don't want to do less than or equal to, right? I want to do greater than or equal to 1. So this less than or equal to, which is the last index, has to get gone. So I want greater than or equal to, right? Greater than or equal to, so this goes here, right? Greater, and this goes here. So this is the first change. We're changing that this is greater than or equal to 1. So this is our second constraint. This is our first constraint, and this is our second constraint. So the second constraint is the instead of the index, if you will, this is kind of our first constraint, right? And this is our second constraint. That's what this is. So second constraint in the loop, right? We're defining what to do. Well, our first value, if you notice, what we've coded in here is size minus 1. So this is size minus 1. So I have my size, let's get that, minus 1, and that is my first value. Size minus 1 is what we want to do. Okay, so this is what we want to do for the first constraint. The second constraint we're checking, this is our check condition, if you will, and that we're checking to see is as long as our local integer, the value that we're getting here, right, our local integer we're assigning to whatever the size is, the starting value, as long as it's greater than or equal to 1, this second constraint doesn't trigger the branch, which basically exits the function. This is the exit of the function. This is when it's completed, right? This part right here. If it's not completed, we want to do something, and this is adding 1. We don't want to add 1, we want to subtract 1. So let's add a minus sign, so subtract, and we want to feed this into here, and we want to subtract 1 instead of add 1. I'm going to feed this back into here, and I want to just get rid of this. So that is our new condition. This is the the part of the loop that increments and decrements. So now in effect what we've done, this whole thing, is we are decrementing, right? We have a for loop that's a reverse for loop right now we've created, and we've done that. We don't need these things anymore. I just want to show you what those are so you understand. So this is what happens when it's finished, right here. When it's finished, we want to do something. And here's something else that we want to do. If I want to keep track of, this local integer value, right? That that is the thing that's counter. This is the counter that's happening here. I want to output this. I want to save this value. This is the index, if you will, right? What this value is. This is outer. So I want to promote to a local variable, and I want to call this local variable outer. Okay, because that's what we're doing here. We're saying outer is what this name is. Okay. Okay. So now this, where do we do it? We want to do it as we go, right? Because as soon as we assign this value, I want to be able to start counting. So here, if I look at this, here's our value, right? And I want to branch with this value and stuff like that, and I want to output. So curious for you is, where would we put this? Where do I want to save this value? Well, I want to do it kind of after, through each of the elements in the sequence. I want to be able to get an output value right here. So this is kind of what I want. And as an example, that's what a for loop does. That's our outer value. So let's check this. If we're going to call this little for loop over and over again, and I want to print it out, let's do a print. To show you, just to demonstrate this, and we're just going to print out this outer value the entire time. Right, this is what we're going to do. And it's not going to sort anything right now, but we're in the process of testing everything. So we're just going to do one of these. All right, and the sorted array is going to equal to the original array right now, the unsorted array. So we're going to say unsorted array. We're not sorting anything. We're just basically counting. Unsorted array, and we're just going to output the unsorted array into the sorted array, the return type. So now, here's a question for you. How do I use a function from a function library? So that's something, the next thing we have to talk about. So if I go back to this, and if I go back to my blueprints, let's look at my grid character, okay, as an example, okay? So here's my grid character, and what I want to do with the grid character is I want to run this sequence, and I want to do it at the event begin place. Let's do that. So when it starts, I want to call my bubble sort. So if I just type in bubble sort, it just appears. Look at that. It says bubble sort. And if I hover over, it says target is BPFL sorting algorithms. It's just available. And this is a beautiful way of kind of reusing some of our functions. Instead of like me having to create a hierarchy, I don't have to inherit anything here, right? I want to make almost like a little class of like a function library that I can use in other libraries, in other blueprints, right? So I want to do the bubble sort, and it needs an unsorted array. So I'm just going to make one for now. So I'm going to call this unsorted array, unsorted, or we'll call this integer array, and let's make it. So here's our integer array, right? And compile and save. What we want to do with the integer array is add some numbers. So my integer array right now is 0. Let's make it an array instead of an integer array. Compile and save. My integer array has no elements. Let's add a few elements. So we'll add in like a few numbers, and we'll put them in some random order. So we'll say 5, 3, 8, 1, 7, 6, 9, right? So I've added seven elements in the array of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's add some more. So we'll add in 5. We'll add in a 4 and we'll put in a 10. There we go. Okay, so that's the numbers that we have right now. Maybe we'll put 10 here. We can move things around. That's the beautiful thing about this thing. So they're hard-coded values. That's what I have here, and I want to make this integer array available so we can see it when we make a grid character, right? Something like looks like this. Yeah. Yeah. So if that makes sense, and yeah. So that's what we want to do. So we want to take our integer array and pass it in to my unsorted array, and then what's going to come out with the unsorted array is going to be the integer array. So we're going to say the integer array, we're going to set this now to our unsorted, where it's going to be sorted. So it comes unsorted and it comes out sorted. That's what we want in our example. Compile and save. But now we don't have any sorting. We just want to see what our numbers are going to be. So if I was to run this thing, right? So go back to here, and if I was to run, then we should have a bunch of values that come up, right? And we can't see them here, but maybe in our output log, you know, as an example, we can see these values kind of run when I'm kind of outputting these values, right? So it says, you know, blueprint user messages 9, you know, as an example, and it kind of happened really quickly. Let's try that again. You can see that it says, like, go back there. It says 9, the value of 9, right? Let's try that again, watch. So there is a 9 value. So what does that mean? So let's go back to the loop and take a look at our grid character. So we have all these values here. So 5, 4, 5, 3, 8, 1, 7, 10, 6, 9, 5, 4, and it outputted one value. All right, so that's not really what I want to do. Let's kind of go to our string here. And so duration is 2. We'll make the duration be 30, and it only prints out our value once. And I'm doing this because I want to show you, you know, where this outer thing should be. Where should this outer thing be? We want to save outer. That's what we're doing, right? So when should we put this in? So if I press play again, you can see that 9 is something that we have there, and it's last there as the number 9, right? So that's what it says, output message 9, right? Which isn't really what we wanted. That's not what we want from this. Like, how can it be 9? Well, 9, if you think about it, is the index of the array, the outer index, which is 9, right? And it hasn't done anything. It didn't do any of this. So it's almost like I've got to wait for the second value to be decremented if I want this to be done. So if I want to see 98765 as an example, then this outer index is something that I got to put in here before I output it. So it doesn't belong here. It belongs here. Okay, I'm going to show you this. I'm showing you this because I want you to understand how you know, to make this thing happen, where this should kind of look like this now. So if I wanted to count the numbers and I want these values to change over time, then this is what I want. Okay, something like this. So if I press play now, and if I press that number, you can see now I still get the value 9 in my algorithm. Well, one thing is that if I stop this, so here again, if it's true, then, because it goes through this area right here, so here's -1, and then if it's true, if my greater than or equals true, then also this is bad, because this only prints out one time, because it can't be here, between here and here, because this just checks to see if it's true. If I'm done, this is the completed condition. That's what this is. When everything is completed, well, then I do this, you know, kind of thing. So that's not good. Okay. So so it doesn't belong there. So let's just take those out of sequence and put those back the way it is. So it doesn't go there, right? And it doesn't go here. But what about if it goes here? I'm just going to make this loop thing happen, because this is kind of what's happening here. This kind of loops through. So it says it goes true. If it's true, then it goes here. and it's out. And then the second thing that it does, the sequence does this, checks this thing first, and it returns. Otherwise, it goes back and assigns this variable right here. Okay, so that's the other thing it's doing. So this part right here is assigning. Let's just check out how this works. I'm going to move this up here. Okay, so I definitely want to print this up, but where do I do it? Do I do it before this part, this check, as an example? And if I do it, then it has to be in here. Okay, so again, it's convoluted, but all I want to do is check this, right? I want to assign this outer value so I can check it all the time. And here, this is just my print check to confirm that it's actually printing out. So let's try this out. So between here and here, I'll kind of put this, and I'll put this, and let's see how that works. All right, so compile and save. And test. 9. All right, so that's what all it does is print 9 again. Huh, that's not it, right? So here is where that's happening. Here, so let's look at all the execution areas that it can happen. It can't happen here because nothing's happened yet, right? And this subtracts 1, right? Size minus 1 is where it starts. And this is where we're assigning values. And this is checking to see if it's greater than or equal to 1. If it is, then it's going to do this. If it's not, then, it's going to, if the condition is false, then it's going to, kind of continue, right? That's what it's supposed to do. So this is the false condition. What happens if, things are happening, right? All right, well, maybe that's when I want it to do it, because if it's false, if it's not greater than or equal to 1, right? So look, so this thing, so size minus 1, right? And, do I want to say that instead of true being out, then it's false that's out, because all we're doing is looping. This is this great loop that we're making, right? So, because again, if I was to go to the original, let's take a look at the original for loop for a second. Here's my for loop. And if I was to output the loop body, this is the loop body, here's the completed, and there's first and last, right? So first index and last index. So if I was going to do from 0 to 9, as an example, right? And I wanted to loop, the index would print out for in the loop body, that's where I would put in, whatever I'm doing. Well, the loop body is, if it's false, isn't it? Well, if that's true, then maybe I got to move this, right? So let's disconnect this and disconnect this. And maybe I got to move this into my loop body. Oh, maybe that's where it belongs. And by the way, I'm saying and doing all this stuff because, this is part of our experimentation. So this is kind of like what we're going to do. So we're going to kind of move this to this, and we're going to move this to this, because, well, this is our loop body. This is what we're going to do, right? But here's something. From an execution pin perspective, notice that if I was to break this up just for 1 second, let's just expand the node, right? Notice that I don't have to go back from my loop body, right? I don't have to go from here. I don't have to go from here to here at all, because remember, as long as I print, I'm good. So this is my loop body right here. Let's see if this is true. Let's see if I'm right. All right, because again, all I want to do is print out the numbers over and over again. Pound save. So if I press play, right, as an example, and let me just make sure that we have kind of condition. Now we get nothing printed, and the reason for it is because we have no execution, right? That's the thing that also has to happen, right? Because if I go back to my algorithm, this doesn't go anywhere. And because this line of execution goes false, as an example, this is what happens when it's false, right? Then it only happens when I'm counting downwards. So this is only going to trigger 1 time, and, well, outer is never going to be assigned, right? Because that's what the variable is. Okay, that's not good, right? So here's something else. Like, notice the variable, right? Here's my assigning a variable, and here's my the in part of my assignment. This is the assignment. Here's my variable in, and here's my value. And then what's happening in this local variable, this is a local temporary integer variable that is something that I want to keep track of. This is what I want to save. and this is what I want to put out, and it's going to happen, you know, I want to save this thing, like, I want to set it and save it over and over again, right? Well, maybe I have to do it in 2 steps, right? Because again, I'm not thinking about things the right way, and you know, it's not my right thing. But false means that, well, this is not true, right? So if I say something like, you know, this is my test. So again, if it's like size -1, if it's 10, -1 is 9 greater than or equal to 1? Well, that's true, right? So if it's true, then it's going to go to this sequence. Then it's going to go, well, I'm going to output something to the node. It's going to exit. That's what I've made it do. This is the true area. If it's false, then it's going to return here as an example, and that's what it's going to do, right? So this is my unsorted array, and this is my my sorted value, right? So let's take a look at this. This is how it's going to work, right? So this is outer, right? But this is if it's false. So if I fail, the test is 9 greater than or equal to 1. And if it's true, then what I want is for me to go here, the assign, and I want to subtract this number here. I want to take the original number and subtract it from this, from -1, you know, kind of thing, right? And then when it's done, I go back here and test it again. I test the number. So this is what's happening here. This is the loop, right? So it's going to go through here. It's going to basically say, okay, so is this is the condition, is 9 greater than or equal to 1? True. Okay, cool. Well, it's going to go here. Doesn't do anything. And if it is true, if it's you know, if this condition passes, then it goes here and then decrements it. So maybe I want to, before I test, I want to print what that number is here. I want to set it, you know, outer. I want to set that value, and I want to print that value out. It's only printing my value one time, but I want to print it out, you know, as an example, you know, over and over again. Okay, so false is definitely not where it should be. I don't have to connect this for now because who cares? I'm just passing out the unsorted array as an example. And then what I want to do is I want to, you know, kind of save this value somehow, because that's what I want to do. Maybe it's here that I got to save the value. Okay, so again, it's a test, right? So let's see how this works. So undo this, put this in there, and then from here, pass it in there. Okay, let's see if this is something. Well, that can work. So again, what I'm saying is whatever this value is, I set that value, right, to the temporary variable, and I just want to print that variable out. And let's see if this, because this condition should run multiple times. I'm in the loop here, right? Let's see if that is going to work better, right? So there we go. So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So it starts off at 8 actually. There's 8, 7, 6, 5, 4, 3, 2, 1. Because it's so 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm missing 10. I'm missing the top value. So this is pretty good. This is what I want, right? But it's not exactly what I'm looking for, because this occurs, right, in here after the first iteration. So after it's passed this first iteration, it prints out, it subtracts 1, and then prints it out. So we're almost there. Okay, so let's undo that and undo this, and then put that back here. And let's see if we go back to there. That's how it's supposed to go. So this is the loop, right? Well, okay, so we test the loop out, right? And we say that if this is greater, then it goes, this is the first time it passed through a loop, and it comes out here, then, well, maybe it's here that we need to do it the first time, because this one will capture the 9 as well. So I want to kind of do it here. And again, I know this is convoluted, and hopefully it's not going to make your brain break too much. But what I'm basically saying is this: do this. Oops, undo. Do this. So set the value here for the first time, and then from there, make it go continue. So this is where I want to do this value. All right. Okay, we don't care about this right now. Okay. And if I press play, I count from 9, 8, 7, 6, 5, 4, 3, 2, 1, but I don't count 0. I don't count 0. And the reason why I don't count 0 is because it counts to 1, right? It goes from size minus 1 when it's greater than 1, right? It doesn't go to 0. And when it's 1, it stops. So it doesn't decrement to 0. So this is the correct place that we want to count everything right here. So this is correct now, okay? And this is where we want to count. Now we don't need to output this. I did this because I wanted to test this. So now we can just kind of loop it in here and make it nicer. We don't need both of these things. Well, we can keep them, it doesn't matter. And make it maybe it looks maybe a little nicer. But this is the loop. This is the loop that we've made so far. So here is where we're counting. We need this outer the outer integer, okay? And this is where we're going here like this. Okay, so this is what we're doing. And we're going to put this one up here because that's what we want. We can organize these nodes a little bit nicer if we want, but for the most part, they're going to be quite messy because, I mean, it was messy to begin with. So this is the negative, is the kind of backwards counting for loop, if you will. We now have a mechanism, right? We now have a mechanism of making this work. And I'm just going to kind of make this a little nicer, just to make it kind of like that. So they're all aligned. There's not much we can do with these for the most part. Here, maybe we can get rid of one of these. And like so. How about, let's try this again. Yeah. And there we have it. Okay, so something like, so now that we have this, so it does this, right, as an example, this is the loop body. So this right here will keep counting, right? And when it's false, it does this. That's when it outputs the final result. This is when it's stopped, all right? So this is what happens when it's false, okay? So we need this output here as well because false is going to say, well, this is when it's completed, okay? But this in here is the loop body. Right, so this is what's going to happen. We can keep doing this. We'll do this, and we'll also change the counter. So right here, this right here is the loop body. So loop body, and this is when it's completed. Okay. So if this is the loop body, going back to our algorithm, we've got this piece. I know it took us a while, but this is the first one. Now this is just a regular loop, right? Because it's like inner plus plus. So we can just use a regular for loop here. So we can say for loop, right? Here it is. And our for loop, right, which is part of the loop body, is going to do this. So for loop is going to use our first index and our last index. Our first index is 0, that's correct. And our last index is outer. So we're going to say outer here. Okay? So that is our inner loop. This is our inner loop. This is our outer loop. And we need inner to be captured. So here we're going to promote this to a local variable called inner, right? There we go. Excellent. And this is what happens when we're completed. See? So here's our inner loop. This is our, if it's false, if we want to do something when it's completed, we can do something or not. For now, we don't care about that. And this is outer and this is inner. What we need to do now in the inner loop, right, is we need to check, make this check if array inner is greater than array inner plus 1. Unless we can do that. So array inner, so we can get unsorted array, right? And we can check for things. So if we test, we get, again, it doesn't matter if we get a copy or a reference, but we can get a copy for now. And if we get a copy, and we're going to say if array inner, right? That's the inner thing right here. If array inner is greater than, right? Because that's what we're saying, greater than array inner plus 1. So unsorted array, right? And then array inner plus 1. Okay. array inner plus 1. There we go. If that's true, we're getting these two values, right? If it's true, then we do the swap. And what we want to swap is array inner and array inner plus 1. We want to swap those two values. So if branch, if that's true, right, then we do the swap. And let's see if we can do the swap. So if I type swap, here's my swap function. And notice I go in A and out B, right? So it's this world context object is what I would need to make that swap happen. So this is something that I want to talk about. Here, swap in and A and B is one thing. If I use the swap here for a second, I wanted to show you this. That's why I'm doing it. Notice that here, swap in and A and B, I don't need the world context object. But because I'm trying to do swap, I'm trying to accomplish this thing here in my bubble sort, it asked me for this. And, well, there is no world context object right now. It doesn't exist. I'd have to pass it in. So it's almost as if my swap is useless. And I have to say this because I want to show it to you, but we can't use the swap in here at all. Just can't do it. So let's swap it like normal. We'll just do the swap. So temp is equal to array inner, and let's add in a temp value. Temp. So we can say that temp, right, is equal to array, array inner. So array inner is this. That's the temp. Okay. And then we want to make this a sequence because it's a sequence of things to do. Here's our sequence. Okay. So temp is equal to array inner, and then the next part of the sequence is array inner is equal to array inner plus 1. So we're going to say set array inner. So array, instead of array, this unsorted array, set array element, right? That's what we want to do. So we want to set array inner, and we want to take this array element inner plus 1, this one, and we want to set this. Okay, so we're going to set the unsorted array inner, which is the index, array inner, to array inner plus 1. That's what we're doing. That's the swap. This is what's happening, or part of the swap. The next part we want to do, that's why it's a little bit more convoluted, is I want to do this next element, which is swap back, right? So we're going to say that the next one is array inner plus 1. So again, it's unsorted array, and we're going to set another value for array inner plus 1. So sort inner plus 1, this one. So inner plus 1. That's the one that's the index we're looking at. And we want to change the item to whatever is the value of temp. Because we stored it in here. We stored it first in here. We saved it. And after we saved it, we killed the original value. And then we swapped it back in. So this is the swap right here. The swap. Okay. And just to show you something, if I did this, and if I right clicked, and if I said something like collapse to function, right, as an example, I just want to show you this 1 second, and then I said something like swap, right, notice world context is back, and that's why we can't do that way, right? So we can't swap, we can't, kind of collapse to function in this way, because we can't access the function library the same way. So this is the swap, right? And this is the comparison. This is basically our case. This is the case that we're always comparing in, right? All right, so then after we're done this, after we're completed everything, then what I want to do is I want to take my, when I'm completed, when I'm done this array, I want to return the sorted array. That's what I want to do. When on complete, after I've done all this swapping stuff, I keep on swapping every iteration until I do that. Let's just check this out and see now what I get. And if I press play, the way to test this is if I go to the grid controller, so grid character, right? And if I look at the grid character for a second and I want to look at my array, here's my integer array, and what I'm hoping to see is the array on the way out is on the array that's ordered. Right now, that doesn't seem to be the case, right? Where it's 3, 5, 8, 1, 7, 10, blah, 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 it's unordered still, right? If it worked, then it would completely work the way it was supposed to. But unfortunately, it did not. So again, it's like my sorted array. I'm setting my sorted array to my original integer array, it's going into my unsorted array and coming out the sorted array, and that's kind of what I want. All right. And I'm passing this forward. So that's the next problem, right? So here's this part, right? So again, when I'm thinking about my for loop and my loop body, at the completed step is where my unsorted array is going to be out. Here is when I'm doing my checking, my unsorted array, inner, and so on, inner plus 1, and this is where I'm actually doing my swap and that kind of stuff. But that's how it should work. I pass in values, and then my array is sorted as I come back out. Okay, so we know that outer is correct because outer is basically giving me our whatever the value of outer is here, and we can, if I want to check that, so this is my, again, checking to see this is happening, we can actually print out the outer value now here. Let's check it out. Let's check this out. So we'll go here and we'll just go to the outer value, right? So, and let's see if we print out. So if I go print string and I want to print outer, and again, this is the check, right? Because I need to print the outer value here. So here's outer, and I want to print this out. This is what I want to do, right? So let's try this out, and let's make sure that it prints for 30 seconds. And if compile and save and test, then we get 0. Okay? 0. And that's why it fails. So we had a value here. Here's our value, but notice it said 0, right? Well, because remember we said this is the loop body, and there's this part and this part, right? And this part triggers, but it does nothing. And then this part actually does the iteration. This is like sets the outer value, which is going to be set to 0 at the beginning. It loops through, but it never changes because this is incorrect. So what if I put this, you know, I kind of did this step, right? And I do it first, right? And then inside here I do this, which is what I want. So kind of disconnect this, put that here, right? And then this is what my inner thing is going to be, right? When I have the outer set, I want to set it up. And if I compile and save and press, then I get 1. All right, so that's what happens. So 0, 1, my message, you know, as an example. And again, if I look at my grid character, or here's my grid character 0, and if I look at the integer array, it's still 3, 5, 8, 1, 7, 10, 6, right? So we're troubleshooting again, right? Because we're able to get the value out this way. We knew this is what's happening here, but as soon as I put another thing in the sequence node, the value gets lost, right? We don't have that value, right? So it's almost like I want to put the sequence this in here, and then the stuff at the end of the sequence, you know, kind of when it's completed, I want to go back to here, right? When it's completed, right? It's kind of what the loop body is going to be, and then, you know, but it's got to be somewhere in here when I'm incrementing is where I want this thing to be, this little thing that's happening here, right? Which is all this. So it's like I want to do this again, right? I set the outer, I want to print it out, it does all this stuff, but then it's going to come back, right? So when it's completed, you know, this is where it's finished, you know, as an example. So here, let's just undo this for a second. And if I say when it's completed, I want to come and do this. Let's see if this works. Do we have a loop again if I do this? Okay, so compile and save. We haven't done it. We haven't done an output yet, but let's see what happens. And if I press play, then we have 87698765432 It says, warning, attempt to access 10 or index 10 from an array, unsorted length of 10, you know, as an example. And that's not what I want because it doesn't exist. But at least it did that when I'm trying to access that element. So it's like 9 minus 1, but I'm accessing array element 10. Let's go back to this. And we're almost there, right? So why? Because, again, outer is going to be set up to size minus 1, so 9, right? And then we're going to try and use outer as my last index, right? So outer starts off at 9, and then, but if I run it as an example, you can see what's happening. This is an important step too, where we can see the execution, you know, kind of here. It only ran once because we're simulating, but if you notice, it kind of ran through this, right? And then it ran through all this stuff as an example. And then when it completed, it came to here, came back into that thing. So it's waiting for it to complete it, and then it comes back there, and then it subtracts 1. Okay, so it does all this stuff, and that's why it did 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, well, if that's the case, and I don't care about the errors right now, but if that's the case, then after I'm done all this, when it's false, then I want to output my array, right? When the case fails, this part, right? When a case fails, then I want to no longer working. I want to output my array to here. Let's see if that works. And if I press play, and if I go back to my grid character 0, and if I look at my integer array, now it's almost there. We're almost there. We're almost in the right spot, right? But let's take a look. Look how it changed. So it went 1, 0, 3, 4, 5, you know, 3, 4, 5, 5, 6, 7, 8, 9. Okay, so that's the new array. It's almost there, but 1 and 0 is wrong. I got 2 5s in here, and let's see if that's correct. Like the original array for my grid character, what did it have? If I look at my integer array, I have a 5 here, and I have a 5 down here, right? So I do have that. I don't have 0. I don't have 0 in my list, right? So that's the first thing. Like my index doesn't have a 0. So where did I get that 0? It did the swap, but I got the 0. Let's take a look at that again and see what's happening. So again, I go size minus 1, so it's 9. If 9 is greater than or equal to 1, it is. Then I come to this point, and then I'm here, and what I want to do is I'm going to get this value, whatever outer is. Size minus 1 was 9, right? And I'm going to say outer, I don't need this anymore because this proves it that I'm actually getting there. I'm saying outer is the value that I'm starting with, which is 9. This right here. So it's actually going in here now. There we go. So this is outer is 9, right? And we're going to say that inner, right, is going to be running. Inner is going to be running, and it's going to be looking at the first value. Now we're saying unsorted array inner, which is 0, starting off with 0, and we're going to say if it's greater than unsorted array inner plus 1, right? Then if that's true, then do the swap. You know, where I take temp, I take the inner, I set it to temp, I take inner plus 1, and you know, I get that, and I set the inner to inner plus 1. That's what's happening here. And then I set the inner plus 1, you know, item back to temp. That's what I'm doing. So this swap looks correct, you know, as an example, and that's happening. This whole thing is happening inside the loop body over and over again. Okay, Now, one thing I could do is, just to prove this out, is I could print this. So let's say print string. Here we go. And let's print out those two values here instead of where we printed it before. So do more testing, because we're almost there. We're not quite right. But we want to do this, and we want to do it right. So let's do it properly. So I want to say that, you know, get outer, this one. And I also want to get inner. I'm just going to drag this in. And I can do an append string, right? So where I want to say outer, here's outer. I want to add a node, add pin, and then inner, oh, sorry, a space, because we want to put outer space, outer space. We want to print out the value of outer. I want a space, right? And then space inner, space inner, space, and then we add another pin, add pin, and we want to print that out. So then we're going to say both outer and inner, we want to print those two values out here. Okay, so that's kind of what we want, and we want to print this for 30 seconds so we can see what those values are going to be, so it helps us troubleshoot. And let's press play. So let's take a look here. Now this is where the important part is. So 90, this is correct, right? 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, and then it says 910, right? So that's where the error is in our loop. There is no 10 because, let's go back to this, we're saying that its outer is the last index, right? But we don't want to have the outer as the last index because we want the outer minus 1. Let's try that. Outer minus 1 minus 1 is the last index. Let's try this for a second. First index is 0, outer minus 1. Let's see if that's correct, because that's where we're getting our first error. Nope. Index unsorted array length of 10. Nope, that's still the same. So it's still doing the same thing. So it's not here that's the issue. Outer, get outer. Get outer. This is correct. This is not the problem. It's this inner that's not subtracting. So size array length is 10, right? Array length 10, that's the size. And then we're using size minus 1 as the value. Size minus 1. Well, let's just do this. So size minus 1. If I did this, so whatever the size is, the array length 10 minus 1 is 9. I'm curious if I plug that value in there, is that going to make, probably won't make any difference at all, but let's see. Can't really see that until we do this. Same thing. So it's trying to plug in. So 9999, and then it goes to 10 somehow. Does it do it again here, or is it one time? 8, 8, 0. So it's, yeah, so it's going 90, 91, 92, 93. So it starts off the end, 99, and then 80, 81, 82, 83, 70, 86, da, 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 and then it goes back to here. But somehow or another, it says that our log script says attempt to access or index 10 from an array of unsorted index of length 10, which doesn't exist, and gives us that error 3 times. So it tries to, it didn't crap out, which is good, but why would it do that? Well, let's do another little test. So let's see what it's giving us here. So that's what happens with these weird things, right? So we'll say print string. Let's do that, print string. I want to see what I'm getting. So again, I'm just troubleshooting. And we're just going to print this out. Doesn't care about that. So it should be 9. That's what I should get. Yeah, 9. So why am I getting 10? It's weird. So this is actually calculating correctly. And then I do the assignment. And I want to take that value, pass that into there. The variable is what's happening here. This is just the temporary variable that I'm using, and I'm assigning the value of 9 to that variable, right? And then I'm subtracting 1 from it, 9 minus 1. And that happens only here, the variable that's coming inbound. Yeah. Outer starts off at 9, but it's like I'm accessing the 10th value, but that must be happening here with my input. I'm coming back to the next value, and it's almost like I'm not able to. So this loop body probably is in the wrong spot. So outer is correct, it goes 9. But what's happening is it's looping 10 times. 9, 8, 7, 6, 5. We're close, guys, but this is kind of what I want to do. This didn't work out. But let me show you what I'm talking about. But it does, for the most part, except for that weird 0 that I'm getting, and I got to do some more troubleshooting here. But for the most part, what it's doing is it's sorting. Not the first value, which is kind of like, and it's also giving me 0 in a value, which of course 0 would be the 10th value because there is no 10, right? And it's going from 0 to 9, and do I even have, I'm missing the last value. So yeah, so it's not quite working, but it's getting there. Look at that, 3, 4, 5, 6, 7, 8, 9. So it's kind of working the way it should be if it wasn't for that weird loop. And it's because of this. It's because of our algorithm, which kind of backwards counts. If I was going to try the other one, right, you know, this one forward counts, and so does this one. The selection sort would have been easier for me to tackle than the other one because there is no negative for loop, you know, kind of a backwards counting for loop, you know, kind of thing. The other thing we could try, instead of doing it this way, is if I was to do a reverse for loop. So if I do for loop, and if I was to do a for each loop reverse, right? If I did this for each loop reverse, and I started back from that, that might save us instead of doing it this way. Instead of doing my own custom for loop, then that might be the way to go. And let's just see if I was to swap this out. I know this is a big change, but whatever. Let's go to there and do one of those. I don't need this anymore. We don't need the completed parts. And what I'm going to do instead is just use a construct that we already have. So kind of pass in the array. So we'll say that this is unsorted array. It's kind of not what I wanted to show you, but it's fine. And it took some time, but at least we figured some stuff out. Here's unsorted array. There we go. And here's my loop body, and what I want to do is I want to save this one as the outer. So this is the array index, right? And all this is just going to be the outer array. We don't care about the array element. We just care about this counting. That's what all this is going to do. And in the loop body, we want to do all this, which is kind of the same thing without actually getting the thing that I wanted, but it's fine. And let's see if that is any better. What's the error that I have? Blueprint failed to compile. Why? Oh, we don't have an output. Yeah, we do all that, and when it's completed, that's why we don't have an output. We could kill the output node. When we complete this thing, we're going to say that add return node, and the return node is going to be the reverse when it's completed. Yeah, that's what it's going to be. So it's going to be the sorted array. Sorry, I killed that node by accident, and that's okay. Here's my sorted array. Sorted array. Why is not working now? Because it exists somewhere. Oh yeah, because sorry, because of this. Because of that. And this will be sorted array. Let's try that. Sorted array. That works now. And then what I want, of course, is the get unsorted array, and pass this out because I've changed the array at this point. And then that should be what I want to do. Compile, save, and test. Yeah, see, we still get this issue, right? And so this is not me. Well, it is me. But what do I get when I get that control character? Good character. 0, 1. Well, it's better. 0, 1, 3, 4, 5. It did the 0 at the top, but the problem with this is that if we looked at our grid character, we have a 10. There is no 0. So 10 is lost. So it's like the last element is lost because this is the array element. Array index is the outer. And let me just check that one more time. So it did 9, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it went to 10. And this didn't change. It has gone to 10 somehow. So that means that the for loop that goes from 0 to the outer, and I still think it's outer minus 1, but because I'm just going to, again, I don't care about this 0 to 0. Let's just see what happens. I'm just curious what goes on. Yeah, so it goes 0. So this doesn't have a, let's clear the on pi. So I'm not crazy. And let's try that again. Clear on pi and clear it. So I'm looking, okay, so 0, 0, 0, that's good. That's how it should be. And I'm just going to curious to do one of these. 9. Yeah. Oh, here it is. So 9, and then it went to 10. Last index minus 1. I guess it would be last index minus 1. Minus 1. Zero, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now what does it look like when I do that? 1, 2, 3, 4, 5, 6, 7. There it is. 1, 3, 4, 5, 5, 6, 7, 8, 9, 10. There we go. That's it. That was it. So it is minus 1. I was almost there, but it was just, and let me just check the algorithm. Maybe I did that wrong. Size minus 1. Ah, here it is. So inner is outer plus 1. That's where it starts off. Inner is outer plus 1 to inner less than size. So this is where the error, oh, that's selection sort. Let's go back to the bubble sort. Inner is equal to 0. Inner is less than outer, right? And that's the problem. I didn't do less than outer. I did equal to outer. And that's because that's what that for loop does. And that's not what it should be. It should be less than outer. And that's why I did this. Okay, good. So that was my error. But we found out how to do it. I don't need to do this. And that we actually did the bubble sort. And that was a very long, non-break kind of thing that I did with a big, long, thing for you. But positive about this is, and let's just clear this error because we shouldn't have that execution pin. We can sort any array now of any length. So if I add in, 13, and I put in another 1 and maybe another 3, you know, as an example at the top there, it doesn't matter the length, because now it should just sort it out, right? So there's 1, 1, 3, 3, 4, 5. Finally, it's working the way it should. Wonderful. But we don't need it to print this out anymore. We don't need this to print out anymore, this part right here. So we are going to eliminate this part because this is not efficient. Save. File, save all. This is not efficient. What we want to do is we want to put this closer. There we go. So that is your algorithm. Okay, your to do. I want you guys to try and do the selection sort, right? Again, the swap will be the exact same that I just gave you, but this part will be different. And try and do the selection sort as a practice run. If you can use your own custom for loop and make it work, I wasn't able to make it work so easily. It's kind of complex. Then go ahead. But if you can't do it, that's totally fine. If you want to use the constructs that are already there, it's pretty good too. So 2 things we were learning from this one, which is, just before we break for a bit with this crazy one, is 1, we talked about function libraries, right, which is kind of an important thing. We made our own function library here, and our function library is sorting algorithms so far, and we can add as many of these sorting algorithms as possible, and it's pretty good. Okay, sorting algorithms, or in this, our function library has to have at least 1 function, and this function can be accessed from anywhere. We also talked about how to break up, you know, expand. By the way, even a for each, a for loop, and if I go to a for each loop, this is a for each loop, right? Even a for each loop can be expanded. Both can be expanded, and once you do that, you have the inner workings of how the loop works. We talked about how to do that. I wasn't very successful, but only because the only thing I messed up was this part, which, you know, was the array -1. The other tricky part is, what's the loop body? How do you get the loop body, and how do you get the completed node? The completed node happens when it's false. The loop body happens before the loop aggregates the result. All right, and that's it for this part. In the next part, we're going to actually do the next part of your assignment